לרוסיה גם. היה טסים פעם, הניסה הייתה מרוסיה דרך ציפיות. אז עכשיו טסים לשם, טסים ממש בין לבין שם, באזור הזה של המדינות לא מפרץ, טסים ממש מעל איראן בין איראן לרוסיה. ממש יש לנו איזה מסדרון כזה קטן לאזרבייג'אן, כל מיני כאלה שם של זה. ממש שם זה בחזרה, הסטודנטים שלי חזרו מקנדה.
זה נראה לי פרדיסה ב10 שעה שעתיים, לא?
כן. כן, מבאס.
היי!
כן, שלום.
שבת מגופות!
היי.
Well,
He came back. He came back especially for you.
Yeah.
What we...
I turned something yesterday.
Oh, from where?
I was 1 week in Japan and 1 week in San Francisco. So like around the world in 2 weeks.
We met in...
Yeah, we met in...
Yes.
Did you ski?
No, I was there actually, was the store. 2 days of secure snow.
אני חושב שזה פועל.
Actually, I almost got stuck there.
זה פועל. איך אני מחמש דעות?
Avalanche. Locked down in the hotel. Tuesday and Monday. I'm just sitting down there waiting for the transportation.
אתה רוצה שאני גם אנהל או שאתה... מה? צריך לנהל? זה? זה מפריע? בוא נפתח קצת אבל...
Don't hold on the stuff.
שלא יהיה...
לא, יש שם
So,
have some good stuff.
Really? Okay.
please take a seat. Well, you can. Okay. So, and yeah, this university has a tendency for doubling names. Originally there were Moti Deutsch and Moshe Deutsch. Now they both retired, so immediately we hired Asaf and myself so that we can, yeah. And we have Yitzhak Rabin, and then we have, yeah.
No, but I don't have anybody.
You know. Okay, so today I'm the host of this special colloquium, and we have Masha, Maria from Max Planck Institute of Light in Erlangen. And she's working on beautiful things in quantum optics. We have partners, and I know what she's doing, and today you will know as well. And she's been in Max Planck for the last 13 years as an independent researcher. Before that, she did her all her degrees in Moscow State University, but that was long ago, and we don't have to dwell about that too much. And Masha, we're very happy that you came, and please, the stage is yours.
Okay. Is there a pointer? I forgot to discuss. But okay, I have long hands.
So we can. Had I known, I would have brought.
I will start, just not to waste time. And if there is
A pointer will come.
pointer appears, then
pointer
that's
will
fine. So I would like to thank Avi for the invitation. In fact, we collaborate quite successfully, and there will be something about it in the talk. I come from Germany. Just wanted to show you so that you should know. The city of Erlangen is not far from the city of Nuremberg, which is, I believe, known to the humanity, and especially now this city is mentioned in connection with the events in Ukraine, so everybody is waiting for Nuremberg. Anyway, this is our institute, Max Planck Institute for the Science of Light, and this is my group. And because I will be talking about just a few things, I want to show you what we're doing in general. Our group is called quantum radiation, so we generate light that has non-classical quantum properties, so cannot be described by classical optics. And most of all, we love to produce photon pairs, entangled photons. We do it, of course, in bulk crystals, but also in fibers through foil mixing, together with Nicolas Joly. Our current very interesting direction is that we produce entangled photons from nanoscale sources like metasurfaces, thin layers, monoatomic layers. We want to generate photon triplets through a direct decay of 114.3. And then we work also in the regime where there are so many pairs that the radiation being quantums is bright at the same time. We call it bright squeezed vacuum. My lecture will be my talk will be a lot about this. With the bright squeezed vacuum, we do nonlinear optics experiments using it instead of the pump. And we're also doing nonlinear interferometry, and I will cover these three subjects in my talk. So this is the plan. I will first explain how under different pumping we pass from generation of pairs to the generation of this bright squeezed vacuum, this radiation. Then I will speak about nonlinear interferometry, and finally how we use this quantum light, this light with non-classical properties, to even do nonlinear optics. So we use our main tool is spontaneous parametric down conversion. It's a nonlinear process in crystals with second order susceptibility, so second order nonlinear crystals. And in this case, a pump photon, a photon of a blue or UV light, can split into a pair daughter photons. They are called signal and idler. Unless we speak about very thin crystals, they satisfy phase matching condition. K vectors of signal and idler should sum up to give the K vector of the pump, and the frequencies of signal and idler photons sum up to the frequency of the pump. Just I want to mention that sometimes this process, oh wonderful, thank you so much. Sometimes this process is considered as the reverse of some frequency generation, because indeed when you generate some frequency, the two photons merge into one, and here they split, one photon split in two. But this is a slightly misleading analogy, because while second harmonic generation is purely classical process, everything can be described by classical optics. Here it's a spontaneous process, and as spontaneous emission of atoms, it needs quantum theory of light for the description. Right, and then this process, this radiation of pairs, can be understood as the noise of a parametric amplifier. And I will speak about parametric amplifiers in my talk. So a parametric amplifier, this is a picture from the internet. A parametric amplifier, rather old. This is a device you can buy, known from the 60s. Known before parametric down conversion was known, and so people knew that if you want to amplify optical signal, you just have to pump a Chi2 second order nonlinear crystal, and then the signal is amplified. But then, of course, not only the signal is amplified, but something else is appearing, and this was called idler because it was seemingly useless. You know, it was just appearing by itself, idle, not doing anything useful. And this is just the difference frequency generation, because the frequency of this idler beam is frequency of the pump minus frequency of the signal. So this is nothing, there is nothing quantum here. The quantum thing appears when, indeed, as I said, if you don't send the signal into this amplifier, you still have the output signal and idler radiation. And it was noticed, it was actually discovered in 3 groups at the same time, 67, published almost simultaneously. I'm proud to say that one of these groups is one where I started my studies at Moscow State University. The 2 other are American groups. So they noticed that at the output, even at the absence, in the absence of the signal and other radiation. There is something at the output. If you put your eye here, you will see this. You shouldn't, actually, just for the students, you shouldn't do it because the pump is rather strong. But you will see this, in the simplest case, concentric rings, rainbow, which is this spontaneous parametric down conversion effect.
So
Yes,
can you just
yes.
explain the notation? Why is it? In what sense is it parametric?
It's parametric because, well, first of all, the theory is similar to the theory describing the pendulum, the parametric, like the swing. When a child is swinging on a swing, the center of mass is lifted and like going up and down twice during the period, and so the length of the pendulum changes, and so you pump energy into this. This is a direct analogy. Here, the pump has a frequency twice smaller in the simplest case than signal and idler. So parametric because the parameter of the system changes. Okay. So again, to explain it, to explain the effect, either you use the quantum theory or you assume that there is vacuum seeding. There are vacuum fluctuations, quantum vacuum seeding this process, and for instance, the vacuum signal photon creates the idler photon through difference frequency generation, and vacuum idler photon creates signal photon through difference frequency generation. But I will not go into this detail. Just let's use quantum theory, and everything is fine.
So the reason you require the quantum theory is because without vacuum fluctuations, you have the pendulum is in the lowest point, and pumping is doing nothing.
Right. Yeah. Good point. Actually, yes. Okay. So this is these pairs that are emitted are the realization of the very old, more than 100 or about 100 years old paradox by Einstein, Podolsky, and Rosen about two particles that are created at the same point with opposite momentums and the same position. Now it's more fashionable to show other three gentlemen. So these are people who got the Nobel Prize last year for works on entangled photons. The entanglement can be of different kind. So these pairs manifest position momentum entanglement in the sense that their transverse positions are the same at the time of birth, and their momentums, transverse momentums, are opposite at the time of birth. So one goes up, the other goes down. Then there is time frequency entanglement or time energy entanglement. If one of them is shifted to the blue, the other one is shifted to the red. The sum of the frequencies equals the pump frequency, but the time both times are correlated. So at the same time they are generated. This is called time energy entanglement. And finally, there can be if you organize the experiment properly, there can be polarization entanglement. Well, the indices 1 and 2 are missing here. So if one of them is polarized horizontally, the other is polarized vertically, but at the same time it can be the other way around. The first photon polarized vertically, the other one horizontally. And these pairs are used in many fields, like in quantum technologies today. They help to provide more secure communication, more high quality imaging, quantum imaging, and faster quantum computation. But I'm not talking about this because I'm going to talk about the situation where this nonlinear crystal is pumped so strongly that there are not just pairs, but pairs overlap, and they become bright beams, or a single beam, bright. And if we put a detector here after getting rid of the pump, we put a detector and just measure the output signal, the output intensity or number of photons as a function of the pump. We see that the dependence is nonlinear. In fact, the number of photons, we usually speak about number of photons per mode. That means per coherence time, per coherence area, per mode. So this number of photons per mode is related to the pump through this value that we call parametric gain. So the number of photons is hyperbolic sine square of what we call parametric gain. Well, some people call parametric gain the whole thing, but there is some ambiguity here. And this gain can be very high, so the overall number of photons can be extremely high. This parametric gain depends on the pump like this. So EP is the amplitude of the pump, so it scales as the square of the pump intensity, and square root of the pump intensity, and also it's proportional to the susceptibility and to the length of the nonlinear crystal. In this case, the parametric gain here is about, I think, 10, if I remember correctly, or 15. I will show some better pictures. Why this happens? Because at the beginning of the crystal, the process is of course stimulated by the vacuum, because there is nothing else except the vacuum. But then as everything propagates along the crystal, then radiation generated at the beginning of the crystal starts to stimulate the radiation further, and then it's exponential amplification. That's how it works.
Question?
Yes?
If the power is pumped up so strongly, then you could imagine that other higher orders of the susceptibility are also important. To distinguish.
Right. Well, we see other processes, but only starting from some level. Maybe I even have some slides on that, I'm not sure. But what happens is, at first we have this clear sinh square dependence, and then the pump starts to, first of all, there is just pump depletion at some point, because we can convert up to 40% of the pump into these twin beams, and then of course into this squeezed vacuum, and then of course some of the pump is missing. But also we see some frequency generation between squeezed vacuum and the pump. This is still Chi2 process. We see harmonic generation from squeezed vacuum. I wouldn't say that we see high order effects, but we see other effects also related to Chi2, yes?
So related, how is that depending on the temperature of the crystal?
Well, normally we use BBO. If we use KTP, then the phase matching of course depends on the temperature, but in BBO crystal there is no such dependence. We don't see effects related to the heating of the crystal, because we usually pump at transparency, in the transparency range. But yeah, for some crystals like lithium niobate and KTP, the temperature has to be controlled, because not Chi2, but the refractive index depends on the temperature and the phase match. And so we see this picture. This is a screen. These parametric down conversion rings are so bright that they even reflect on the optical table. So when I say bright squeezed vacuum, I mean that there are so many photons that they overlap, but the radiation still has quantum features. And yes?
So at some power, some amount of power, you will lose quantum behavior, right?
Yeah, that's a very good point. That's a very good point. We actually see quantum behavior up to very high powers, and I'm talking about this now. So there are two groups of quantum effects. One is related to one appears in the case where we have distinguishable photons. Idler and signal go into either at two different angles or at two different frequencies, and then we can measure the numbers of photons in each beam up to some uncertainty, of course, because we use detectors that do not resolve photon number, but let's say distinguish 1 million from 1,100,000, right? And then one quantum effect is this photon number correlation. So if we look for the variance of the difference of these photon numbers normalized to the sum of the mean photon numbers, the total mean number of photons. This is called noise reduction factor. And you know, theoretically, ideally, because each idler photon has its signal twin, ideally this thing is zero, because the difference number doesn't fluctuate. In quantum mechanical terms, I can say that this operator ns minus ni commutes with a Hamiltonian. This is for theoreticians. So this this parameter doesn't fluctuate, doesn't have any fluctuations. But in reality, of course, the detector has finite quantum efficiency, and then this result will depend on the quantum efficiency, but it will still below 1. even at bad detection. And this one is called the short noise limit, because this is what you get if you just split a coherent beam on a beam splitter. And I can tell you in reply to your question that we see this behavior, this noise reduction, up to numbers of photons per pulse. Typically this is pulse pump, so up to numbers of photons per pulse of several thousand, and up to values of gain of about 3 G, this G. So we cannot observe this non-classical behavior at 10 to the 10 photons.
Why?
And why? And the reason is that this process is multimode. So there are many modes, and if we detect not exactly the same numbers of modes in signal and other photons, then there are unmatched modes.
What are modes?
What are modes? Well, you can imagine a mode as a single frequency and a single direction, like K, X, K, Y, K, Z, and also polarization. In practice, you can choose modes in different ways. For instance, you can speak of coherent mode, some volume in phase space where light is coherent with itself. So you can choose modes in different ways. What we do in practice, we put some aperture here and some aperture here, and the larger the apertures, the better, because then you have more modes and the mismatch becomes relatively small. Yes?
If I were to look at all the directions, so what is different modes, or if you want different frequencies? I mean, what is how does it look like? I mean, which frequencies? Is it sort of where exactly the same frequency for the idle and this is maximum or something like that?
Yeah, unfortunately, I didn't show this distribution, this slide, but and there is no whiteboard. But I can try to explain. So signal can be anywhere, idler can be anywhere. There is a relation between angle of emission and the wavelength.
Sure.
So in the collinear and about frequency degenerate direction, that's where the frequencies are the same. There is still a bandwidth of about 50 nanometers spectrum and about 1 degree angular divergence. But then there are these branches that go in one direction to the pump frequency, in the other direction to the infrared, and only resonances.
Sure, but that's when you fix the direction. But I'm asking if you were to collect photons from everywhere. So where, I mean, is there any preferred frequency then?
No, just the best, the preferred frequency is half of the pump, just because because everything scales.
That's what I guess. Yeah.
Everything scales as the product of frequency idler, frequency signal. So the best condition is when they are equal.
And there is also degenerates, probably counting, simple counting will give that.
Yeah, but so if you go to the regime where one photon is near the pump and the other is terahertz, then you have very low efficiency. Yeah. So this is one non-classical feature. Another non-classical feature appears when both photons are emitted collinearly with the pump and about with the same wavelengths. So single into the same mode. We say into the same mode again. What is a mode? But at the same frequency in the same direction. And then what happens is the so-called quadrature squeezing. And I don't know how familiar is this audience with the quadratures, obvious group of course, but I can explain in very simple terms. You know that electric, yes?
Yeah, just my ignorance. The pump is coherent.
Yeah, pump is a coherent beam. Usually for such strong regime we need pulses. Pulses are, our pulses are not Fourier limited. So the coherence time is smaller than pulse duration, picosecond pulses. In transverse direction, roughly coherent. Yeah. So electric field, there is a complex electric field to describe everything, but the real electric field is real. So there is this phase plane where we can show the real part of the electric field, the imaginary part of the electric field. But in quantum mechanics, these values correspond to operators' position and momentum, and they do not commute. And there is a way to roughly show the joint distribution, because for non-commuting variables there is no joint distribution. You cannot say the position is such and the momentum is such. They cannot be measured. at the same time. They shouldn't be even considered at the same time. That's why there is one attempt to attribute some joint distribution to position and momentum, and this is the Wigner function. So this and it cannot be considered at a point. It always has an uncertainty. So, for instance, the vacuum in quantum mechanics is just a Gaussian distribution around the center, and it has the minimal possible width if distributed equally. And the state that is generated this way looks like this. So it has one uncertainty reduced and the other uncertainty increased because of the uncertainty relation. So the uncertainty in this direction is small, in this direction is large. And this is called squeezed vacuum, apparently. Vacuum because it sits at the center, squeezed because it has one quadrature squeezed. And then just to, this is the condition for squeezing. Just to distinguish three cases, I want to distinguish three cases. One case where we have just pairs, and then the parametric gain is very small. The mean number of photons, remember, is this sinh squared, is very small. The Wigner function is hardly changed. It's still Gaussian with equal uncertainties. But then if we increase the parametric gain to about 1, the mean number becomes also about 1 to 10, well, sinh squared of 1. And then we have this squeezing. And finally, the regime where the gain is larger than 1, typically 2, 3, we can have it up to 15, actually, in our experiment. Then the mean number is much larger than 1. And then the distribution is very squeezed. This squeezing is easily lost because of the losses. And then in this direction, it becomes almost the vacuum. But in this direction, it's very anti-squeezing. This is called anti-squeezing. It's very large. And this is manifested in some effects that we observe.
Why is it squeezed in this way and not the other way?
Actually this thing rotates because this is a stroboscopic picture and everything rotates with the optical frequency, of course, like the analytic signal that I showed. Yeah. So next half period this will be squeezed. Okay, so I pass to my second part, which is the nonlinear interferometry, and it is, yes, please.
Can you measure this squeezing?
Yeah, we can. And one method is provided by Avi, and I will show you. Well, actually, the standard method is homodyne detection, but okay, I will talk about it. So the second part of my talk is about, first of all, parametric amplification. I return to this subject. And I want to specify two different ways, just two different versions of optical parametric amplifier. So in both cases I consider Chi2, doesn't matter, some other people consider Chi3. But if we have two different modes into which signal and either are emitted, modes I mean again directions or wavelengths, and two output modes. And if only one input is existing, so for instance I send the input beam from this direction, the amplification occurs regardless of the phase of this input beam. So now I'm considering the case where I really amplify some real signal, some real laser radiation and so on. So if I send my coherent beam from just one direction, then the amplification occurs regardless of the phase. But if the case is collinear degenerate, so I send my input beam from with the direction of the pump and at half of the pump frequency, then the amplification or de-amplification happens depending on the phase. It's called phase-sensitive amplification. And I will speak about this case. By the way, here, if we have both beams, it will still be phase-sensitive, but if only one is present, then phase insensitive. Okay, so I come back to this phase space, position, momentum, and the equations that govern this phase-sensitive amplification are written here. So basically, it's one equation. The output photon photon annihilation operator that corresponds to the complex field depends on the input using this equation. This is called the Bogolubov transformation, and this is the parametric gain that I mentioned. And then if we pass from A and A dagger to position and momentum, then the equations become even simpler. So the position is amplified and the momentum is de-amplified. And this means that the product of position and momentum is constant, and the evolution that a parametric amplifier performs occurs along these hyperbolas. Yeah, xp is constant. And this is how squeezing appears, because if the input state is the vacuum, then we can take every point of this. This is just the idea how it happens. So if we take every point of this distribution and propagate it along the hyperbolas, then of course we get a squeezed ellipse, and this is what we get. Also, if we have a coherent state somewhere here, it becomes de-amplified, and if we have a coherent state here, it becomes amplified. That's why it's called phase-sensitive amplification.
The Wigner's function of the squeezed vacuum is positive?
Yeah, it's positive. It's always positive. Yeah, Wigner function being negative is one of the sufficient conditions for light being non-classical, but it's not a necessary condition. It's just a sufficient condition. So it doesn't have to be negative. But in this case, it's positive. Yeah. Right. So, and then the model that I like to use, it's just a visual model of what this parametric amplifier does. It's as if this is drawn on a rubber sheet. This Wigner function is drawn on a rubber sheet, and I'm just stretching it in one direction, and of course it gets squeezed in the other direction. And this helps to understand the evolution of the Wigner function through this amplifier. I will use this picture in the future slides. So this is how our lab parametric amplifier looks. Very simple, in a very simple case. So this is the nonlinear crystal, BBO nonlinear crystal. So this is a BBO typically nonlinear crystal, or PPKTP, or PPLN. We pump it by picosecond pulses. Here, for instance, at 400 nanometers, and then we get squeezed vacuum at 800 nanometers. If we image the far field of the emission by a lens, we see this typical picture that I showed at the very beginning. It is multimode, as I said. So what does it mean it's multimode? It means that this radiation is not coherent, neither in time nor in frequency. The pulse of squeezed vacuum is not a Fourier limited pulse. It has fluctuations inside the pulse, and the spatial distribution is not coherent overall. So yeah, and it means that it has multiple modes. And this is the typical picture of how the sinh square dependence looks. So the pump energy per pulse increases up to 0.5 millijoule, and this is how signal changes, the output signal exponentially. And here the gain was, the maximum gain was about 15. That gives us 10 to the 13 photons. It's like a laser. It's the brightness of like one of a laser. So this parametric amplification has some very nice features. I want to list them here, but on one of them I will dwell a little bit longer. So first, it was known since long ago that this phase-sensitive parametric amplification does not increase additionally the noise. So for instance, in the case of phase-insensitive amplification, the initial coherent state is amplified, but you see that it gets additionally noise, so the noise is large. In the case of a phase-sensitive amplification, the product of the uncertainties remains constant, and this means that a phase-sensitive parametric amplifier doesn't bring additional noise. The second feature that also theoretically was known since the 90s, this is a theoretical paper with a proposal, that if we, before measuring some state, amplify it with a phase-sensitive amplifier, we protect it against loss, because we can measure the anti-squeezed quadrature. And this is answering the question of how squeezing is measured. This is a scheme of homodyne detection, which I will show in more detail later. some coherent beam overlapping with the state, and then two detectors and the subtraction of the signals. And if we measure the anti-squeezed quadrature, then it doesn't matter if we have some loss. And loss in optics, in quantum optics, is described by just a beam splitter that splits part of the energy, and as we say, the vacuum enters. So when something is lost, then something has to enter, and what enters is called the vacuum. So from this loss we can protect by preamplifying a quadrature that we need to measure. And this was known, and we use it actually. Yeah. But most interesting feature that I want to talk about is from the work by Avi. And the point is that this parametric amplifier can actually replace this homodyne detection. We can do without homodyne detection by just using parametric amplification. So now I'm explaining what homodyne detection normally is. Now suppose we need to measure the Wigner function, the probability distribution for a state psi. We have to send here the local oscillator. It's just a coherent beam that has to have the same properties as the state under test, so the same wavelength, the same pulse shape, spatial distribution, and so on. We mix them on a 50-50 beam splitter, so 1/2 of each beam goes straight, 1/2 goes into this channel, and then we subtract the photocurrents of the two detectors, so the signals of the two detectors. And I don't have space to derive it, of course, but this difference, the difference of the photocurrents turns out to scale with quadrature x cosine of some phase, and this is the phase of the local oscillator. This phase that we can change here. Cosine of some phase times the x quadrature plus sine of some phase times p quadrature, and this can be defined as an arbitrary quadrature. And then the problems with this is that the local oscillator should have the same spectrum and all properties, and what if our state is very broadband, and what if our state is has multiple modes, so multiple coherence volumes and so on. So we cannot do it. And in addition, the detection efficiency has to be high if we, for instance, want to measure squeezing. If the detectors are inefficient, then we are lost. So in this group, few years ago, they noticed, well, this is the way I explain it. Maybe I doesn't like this explanation, but my explanation is that the mean number of photons at the output, the quantum mechanically number of photons is x squared plus p squared minus 1/2, right? The quadratures are, one of the quadratures is amplified by this optical parametric amplifier. So e to the 2g appears, g is this parametric gain, and the other quadrature is de-amplified. And then there is 1/2, and if we amplify this thing very much, then we don't care about this and about 1/2. And then we can say that the mean number of photons after the parametric amplifier scales as the, there is a typo here. Actually, it should be mean value of x squared. Yeah, sorry about that. I noticed only now. I showed this slide to many times already.
Well, that's true also.
No, that's not true, because mean x is 0.
No, you're right.
Because mean x is 0, it's basically the measurement of variances, and the short noise level can be found by just blocking this input and measuring the amplification of the vacuum. And there is no need for local oscillator because this parametric amplifier acts as a local oscillator. Okay, so our step in this direction, and this is our joint project with this university, is that we decided to extend it to tomography. So what we do, we can amplify some state, and the state I show here is a very quantum state with a Wigner function negativity. This is called the Schrödinger cat state. so it has this structure and the negativity, and the strategy is to stretch it by this rubber sheet in all possible directions. So for instance, if we stretch it in this direction x, it becomes like this, and it becomes so thin in this direction that basically this distribution doesn't matter for the photon numbers. All that photon numbers depend on, photon number distribution, is this distribution along this quadrature. And then we stretch it along another quadrature, and again the distribution along this quadrature, marginal distribution, gives us the photon number distribution. And by repeating this stretching along all possible quadratures, we find the Wigner function. So this is our setup, very simplified. We have first optical parametric amplifier, second optical parametric amplifier, and we do spatial and spectral filtering. Spatial filtering we do with a fiber, single mode fiber. Spectral filtering we do by using a monochromator. And out of these modes, which are about, I think, 300 in total, 300 angular and frequency modes, coherence volumes, so to say, yeah? We cut off a fraction of one, but because we don't care about losses at this stage, we can filter this mode and then do, we can filter this mode after the amplification. Right, so this is how from pulse to pulse the numbers of photons per pulse look. So they fluctuate a lot, and they have a distribution like this. So the amplified quadrature has this distribution of photon number, and the de-amplified quadrature a similar distribution. But if you look at numbers, they are very different. So the de-amplified quadrature has a mean photon number, well, actually it's about 10, will be seen further, and this has mean photon number about 1,000. And then from this we reconstruct, so not reconstruct, because the quadrature squared, we can calculate the distribution of the quadrature itself, and this is how it looks. So the amplified quadrature looks like a Gaussian, the de-amplified quadrature looks like a Gaussian, but this Gaussian is much narrower than this Gaussian. And then we do this for all quadratures by scanning the phase of the pump. It's not shown here, but we scan the phase of the pump. If you're interested, I can show the experimental scheme, and we reconstruct this Wigner function without any additional assumptions. And we still get 7.5 dB squeezing and 8.4 dB anti-squeezing, so in this direction, with a purity 91%. It's a very high purity for such experiments. With homodyne detection, it's very difficult to get this purity. But the detection efficiency with an account for filtering is only 3%. So we lose 97% of the signal, because we, even for one mode, we lose 97%. Because of the very narrow band filtering in frequency. And this, I think, demonstrates the advantages of this method.
So yes. Why do you filter in frequency and not just
because we want a single mode. Because
no, I understand, but why you don't use a spectrometer so you can measure?
We use a monochromator.
Yeah, but then you cut in the...
Well, if you could measure everything at the same time. If you had the spectrometer.
Yes, that's what I'm saying, yeah.
Right.
Like simultaneously measure.
Well, in this experiment we just, well, you still cannot measure all frequencies, because to select a single mode, again, I said that a mode is a non-trivial concept, because for a squeezer, eigenmodes are coherent modes, and they are not monochromatic modes. They have complicated shapes. They are Hermite-Gaussian modes. And to select a single Hermite-Gaussian mode is very non-trivial. So you need nonlinear optics basically for this.
That's why you cannot use just a spectrometer. Yeah, it's not going to be like one-to-one for the spectrometer.
But in the future we want to how to say, we want to split spatial modes into spatial modes with big losses, but we are sure that we can do simultaneous characterization of different spatial modes, because there are mode sorters in space. They are lossy, but we are going to do it, and this is actually very important. Another thing we want to do is we want to do tomography of a non-Gaussian state. So this is an example of a single photon that is squeezed single photon. It's a state that on the one hand is bright, so the mean number of photons here I think is about 10, 15. On the other hand, the Wigner function has a negativity, and such states are very fragile to loss. But this method allows to retrieve the Wigner function regardless of the loss at the detection stage. And so this is the idea. We stretch it in different directions, and the photon number distribution is given by just the marginal distribution of this quadrature that is amplified, and then we can reconstruct, not reconstruct, but calculate from this the probability distribution of the quadrature, and we do it for all quadratures, and we hope to reconstruct this Wigner function. We are doing this experiment now. One more thing is nonlinear interferometry. So I spoke about parametric amplification. So how much time do I have? Should I probably jump through maybe?
We have something like 15 minutes.
50, really? With questions? Because it's more interesting to answer questions.
Mm-hmm.
I wanted to show, well,
we're asking as we go, so.
Very briefly, I wanted to show that if there are two of such parametric amplifiers and there is some phase disturbance between them, no matter if it is in the pump or in the signal light, in this down-converted beam, the sensitivity to this phase disturbance is much higher than it would be for a linear interferometer. And this was actually demonstrated in 2014, although it's known for quite some time. The idea is as follows. So the output intensity, as we change the phase, will oscillate, because for some phases the second amplifier will further amplify what is generated in the first, and for some phases it will de-amplify. And then the sensitivity is calculated like there is uncertainty, there is an experimental uncertainty of measuring the output intensity, and there is a slope. And if we divide the uncertainty by the slope, we get the phase sensitivity. And then for this nonlinear amplifier, the slope is much higher than for a linear amplifier, because the amplification is nonlinear. Yes, how to say so? This is a linear interferometer, and this is a nonlinear interferometer. And while the uncertainty somewhere here is similar, the slope is different. And that's why we can overcome the short noise limit. The short noise limit given by the what happens with the coherent light and usual interferometer. And in addition, as before, if we amplify enough, we don't care about detection losses. So the detection efficiency can be basically anything if we can amplify enough. And we demonstrated this for this SU1. This interferometer has a name, SU11 interferometer. So first crystal, second crystal. We demonstrated that the phase sensitivity remains better than the short noise level until like detection efficiency of about 15%. We still had this detection efficiency better than the phase sensitivity better than the short noise. And then in another experiment,
what do you mean by that?
What I mean by that, short noise sensitivity is what is given, is what you get if you have a usual Mach-Zehnder interferometer, linear interferometer, send coherent light, and the short noise sensitivity delta phi is 1 over square root of the mean number of photons inside the interferometer. This is called the short noise level. So this interferometer allows better.
Yeah, no, but the next graph.
Yeah, the next graph. So here is the level that
so why it is depending on the detection?
Because the worse your detection efficiency, the worse your phase sensitivity. But you can, but by increasing the amplification of the second parametric amplifier, you can always improve it. So this, for instance, is weak amplification. I forgot what was the parametric gain. This is stronger amplification, and this is very strong amplification. What matters is actually the difference of gain 2 and gain 1. And in this case, it was about 3, I think. The gain 1 was 1.5, gain 2 was 4.5, something like that. So in this case, we artificially reduced the detection efficiency, and we could go very low in the detection efficiency and still overcome the shot noise limit. And another experiment, which I'm not showing, I just show the result, where we used a usual Mach-Zehnder interferometer, but after the interferometer, before detection, we amplified, and again got a subshot noise. Well, the usual Mach-Zehnder interferometer fed with squeezed light, so like what happens in LIGO, for instance. And we amplified it before detection, and we got again this amplification. So I'm really running out of time. I want to mention just the last thing about this nonlinear interferometry. And namely, there is a very fashionable subject, sensing with undetected photons. It's based on the fact that if you have this one amplifier followed by another amplifier, and signal and idler photons differ in frequency, for instance, then you can introduce some phase or absorption into one of them that probably is at wavelength that you cannot detect very well, but you can detect the other wavelengths. Yeah, for instance, this can be in mid-infrared, and this is visible, for instance. And you don't want to detect mid-infrared, you want to detect the visible. So you can measure something happening in this channel by only looking at the visible wavelength. With the phase, it's clear, because as I showed you, the signal here, no matter in this detector or in this detector, depended on the total phase inside the interferometer, signal plus idler. But with absorption, is less trivial. And there are lots of works in this direction, but most of them are in the case where the parametric gains are very low. We do this with the parametric gains reasonably high, and so that's why we call it sensing with many undetected photons. So there are many photons here, right? And why is it better? Because we have higher sensitivity, and because we measure amplified signal. If the gain is low, then it's just interference between the pairs generated here and the pairs generated here. But if the gain is high, we amplify the signal before detection, and the intensity hitting the object here can be low, while the intensity measured by our detector is high. So this is an advantage. And well, in this slide I have a very complicated setup, which I don't want to. Probably it's boring to explain this setup, but I just want to say that here we generate broadband twin beams, signal around 800 nanometers, idler around 1500 nanometers, and we use the folded scheme. So in the same crystal we generate squeezed vacuum twin beams, and then we send both back into the same crystal, and we detect the visible to learn something about the infrared. And the result is that we can do optical coherence tomography and FTIR, Fourier transform spectroscopy. And these are some first preliminary results. So we see, for instance, in terms of optical coherence tomography, we see we have the resolution like less than 10 microns, maybe 5 microns. And in terms of Fourier transform limited spectroscopy, Fourier transform spectroscopy, we measure some filter at 1500 nanometers by detecting only visible signal. And so I'm coming to the last part, which is pumping nonlinear effects, and it will be very short. So, as I said, this figure also rotates with optical frequency. And then, if we plot the electric field, then sometimes at some time moments the fluctuations are increased, anti-squeezed, and at some time moments they are squeezed. This is the short noise level. And while the squeezing is very sensitive to loss and doesn't survive even very small loss, this anti-squeezing is robust, and it's really difficult to lose it. And this helps to enhance nonlinear effects. So if you consider multi-photon effects, like for instance nth order effect, like nth harmonic generation, then the rate of nth harmonic generation obviously scales as nth power of the mean photon number at the input. And then when you average this thing, you will have to, you will obtain this factor in front, and this is the nth order correlation function. So the mean, the averaged nth power of number of photons, this is normal ordering, you can omit it if it is classical, normalized to the nth power of mean photon number. And this Gn is high as long as, whenever photon number fluctuates, then this Gn will be high. It was known for a long time that even for thermal light it's very high, and also it was known that for bright squeezed vacuum it's even higher. So for bright squeezed vacuum, Gn is 2n-1 double factorial. That's the product of all odd numbers up to 2n-1. So for instance, the G2 is 3, but G4 is 105. And this is how these nth order correlation functions grow with the number. For coherent light they are all 1, but for thermal light it's n factorial. For bright squeezed vacuum it's even faster.
What is a thermal light?
Thermal light is light from thermal sources, light from the sun.
So
from the sun or from the laser below threshold. A laser below threshold emits thermal light. It's just light with fluctuations. Just fluctuations. But bright squeezed vacuum has stronger fluctuations. So Gn is even higher. And you see that even thermal light provides advantage in the rate of multi-photon effect compared to coherent light. But bright squeezed vacuum provides even higher advantage, even stronger advantage. And we demonstrated it rather long ago now by generating second, third, and fourth harmonics from bright squeezed vacuum. And this is a comparison with coherent light. The advantage in the case of fourth harmonic is about 2 orders of magnitude.
Compared
yes.
with the same intensity?
Yes. Compared with the same intensity. Sorry. Yeah. So this is the flux, bright squeezed vacuum flux. This is coherent light flux. Yes.
Do you need a spatial? I mean, but the spatial. This is the longitudinal mode, the temporal mode. What about the spatial mode? I mean, it has to be 1.
No, doesn't have to be. Actually, this is a good question. In the simplest case, you can imagine pulses, single spatial mode, but just fluctuating from pulse to pulse. But harmonics are instantaneous effects. So if these fluctuations also happen inside the pulse with very high, with very short times, harmonics trace them, and the effect is there. And the same in space. The spatial distribution can be like speckle. It's speckles in space. Right. So we demonstrated this advantage, and also even more interesting is that this is the photon number distribution of bright squeezed vacuum, red points. It has this broader distribution than, for instance, thermal light, and much broader than coherent light. Coherent light has Poissonian distribution, thermal light negative exponential distribution, bright squeezed vacuum even longer tail. But if you, for instance, look how third harmonic from bright squeezed vacuum looks like distribution, it has so-called heavy tail. So this is the double logarithmic scale, and this is log linear scale. In log linear scale, compared to thermal light, you see much longer and heavier tail. And then if you look at the pulses one by one, at the statistics of light pulses, and this is the mean the number of photons in a pulse, normalized to the mean number of photons. So the mean number of photons is somewhere here. Sometimes there are events that exceed in value like orders of magnitude, and this is called rogue wave behavior or extreme events behavior. This is, well, if you observe waves in the sea, for instance, you can expect that if the mean height of the wave is 5 meters, then you probably can see 10-meter wave, but you cannot imagine that you see 100 meters, and yet it happens. And this is called rogue waves. Yeah. So we saw these effects, and another case of multi-photon effects is what we do currently together with Peter Hommelhoff from our university and Ido Kaminer from Technion, is we use nanotips and we shine pulses of squeezed vacuum and we kick out electrons. And each electron, the so-called work function is high, so that we need 4 to 5 photons for a single electron, and that's why it's a multi-photon effect, multi-photon ionization, if you want. And we look at the number of electrons at the output, and we see that while for Poissonian, for coherent light, the distribution is Poissonian. Here it has the same heavy tail and also higher efficiency. Well, I think I used all my time. Just before concluding, I want to thank people who did the job. That's my postdocs Kazuki and Alex, my PhD student Mahmoud, and also former students and postdocs Gaetano, Kirill, Mathieu, and Sasha, and my current collaborators, Peter Hommelhoff's group, Farid Khalili. Yeah. Thank you for your, well, I just summarize. So I showed you transition from pairs to squeezed vacuum. I showed you, this is my most, my favorite experiment out of this, the tomography, using parametric amplifier and the multi-photon effect. So thank you for your attention. Sorry it was long, but the questions came during the talk.
Any more questions?
When you were talking about tomography, did you mean just measuring Wigner function?
Yeah, there are different.
Is it interesting by itself? Why do?
It is interesting because a lot of quantum optics is about preparing non-classical states of light, and most interesting are non-Gaussian states with negative Wigner function. And it's very important to characterize these states. And also it's very important to characterize these states in multiple modes, because there are some protocols of how to use multi-mode states, and especially multi-mode non-Gaussian states. Yeah. Yeah.
So just qualitatively, what causes these extreme events of?
It's very simple. If you have initially fluctuations of photon number, and then it undergoes nonlinear transformation, so the output nonlinearly depends on the input, and of course the fluctuations are stronger.
The events of high intensity become more and more important if you're you're raising it up to the power of 6.
Yeah.
Oh, but I wanted to ask a question about the same thing. How non-classical is this?
You mean the non-linear optics with these extreme events?
Yeah, the extreme. I mean, indeed you have a way to generate light with high fluctuations, but those are fluctuations of the anti-squeezed quadrature.
Yeah.
So,
from my viewpoint, it's just statistics. It's not quantum. Yes. There is nothing quantum.
So if we could do this from, I don't know, if we could generate some clever lamp or some trick to do this with completely classical light, we could get similar things.
But it's still better than a lamp. It's still better because these fluctuations are super fast.
Okay.
So because the typical times of fluctuations are given by the inverse bandwidth of the process, and the bandwidth can be very high, and so the typical times can be few femtoseconds.
So you're saying if you could do this electronically, yes, but that would be, I don't know, nanoseconds or less.
Yeah, but a modulator cannot do it. Yeah,
understood.
Yeah, but I keep repeating, this is classical, and yet my colleagues at Technion find it very interesting, for instance, because they want to generate, we also want to generate high harmonics, and high harmonics has interesting features. The typical plateau that is observed in high harmonic generation gets broader if you pump it with squeezed vacuum or even with thermal light.
Yes.
Or they look at the evolution of electrons, theoretically so far. So I think that's very interesting.
Okay. Yeah, last one. I mean, of course, if you have more questions, then stay, but we're getting late. So yeah, last one, please.
Okay, just how do you make this cat state?
The cat state, the only known way for me of a cat state is when they take a cat state is an odd photon number state. The state that I showed has odd photon numbers 1, 3, 5, 7 and so on, but no 2, 4 and so on. So how they make it, they take squeezed vacuum, which has only even numbers like 0, 2, 4 and so on, and do what they call photon subtraction. So they put a beam splitter, very weak beam splitter, and take pulses from which one exactly photon was reflected, and then they come from even to odd photon numbers. But this is called a Schrödinger kitten because it has very low number of photons. And then some people try to breed these kittens to amplify it, to make it.
Yeah. Okay. So I think yes, Maria, thank you very much. Maria is with us for the day, so if you have more questions, you can still find her. זה הוקלט עכשיו, ברגע שתדבר עם מזכירות, אתה רוצה את זה מהר?
תוך חצי שעה.
אני מבקש מנירית את הלינק ואני אפרסם אותו.
שאלה, יש לך מקום עדיין על הסדר יום למחר נגיד?
מחר קצת עמוס, אתה רוצה, אתה יכול להשתחרר היום.
להשתחרר היום, באיזה שעה?
5:15.
5:15.
Thanks very much.
5:15 זה שכבר מתה...
I hope you have a good coat.
לא, 5:15, כעיקרון אני הייתי לפני שאתה חושב, אבל אני לא צריך את זה, אנחנו מדברים הרבה ואני גם לוקח אותך אחר כך לאכול. אז אני give up my...
Yes, I know.
תפקיד את הפרשים שלהם.
So I have to look into my computer every time, my schedule.
אוקיי. אם כן, אז צריך להגיד.
It's a shame I didn't tell properly about this Wigner function, because it's my favorite really, this experiment with tomography. I was a bit out of breath after answering questions, and I think I scrambled it a bit.
I was not under this impression.
Did you understand?
He understands Wigner.
Mainly for you.
What? I
so
enjoyed it and I understood. Let's see, do I need to turn it off or something?
I just love this method that they invented, of this parametric homodyne, as they call it.
Right.
And yeah.
I don't know how to turn it off. Maybe like this.
What do you?
Yes.
Not really.